Hello, everyone. Welcome back. Gonna keep the intro short. There are the top three things to ever come out of England. The first one, football. The second one, Dishoom, love it. Third one is this cutie patootie problem right here from the British Maths Olympiad round two. And I'm gonna walk you guys through it, demonstrate the useful ideas you can take away from this problem. So, let's get straight in. Matthew writes down a sequence of positive integers. Each of them is the smallest integer that's different from every integer that's come before it, such that the mean of a1, a2 to an is itself another integer. Prove that the sequence, we're defining a new sequence given by ai minus I, and we're asked to prove that this sequence contains every integer exactly once. So, okay, I'll make some things about this problem a little bit more clear. Let's open up the pen. Okay, so, well, not much really to it. It's mostly straightforward. I guess the condition, the mean of the terms is an integer, would be we want the sum a1 plus a2 all the way to an over n. We want that to be an integer, or in other words, we want n to divide this sum. So, okay. Now, your first instinct might be to just go full caveman mode, no thought, and write down Matthew's sequence. So you're writing down 1, 3, 2, or the next one would be 6, and then it's something, I don't know. Because that's what I did. Back in, I think it was year 9. It was a little jit, must have been this size. I tried this problem. I started at 8 o'clock. 8 became 9, 9 became 10, 10 became 11, 11 became midnight, and I finally solved it. But this was how I started. I took a page and I just wrote down 50, 100 terms of Matthew's sequence. Not a clever idea. So how do you start with these questions? Rather than going straight in, we want to do something which I call take a touch, step back, calm down a bit, and approach the problem from a different angle. What is this angle going to be? Well, we have a lot of strict conditions imposed. And probably the weirdest one is this condition here. The mean of the terms a1 to an is an integer. That's pretty weird. I don't think you'll see many questions asking you that. So it makes sense to focus on this one first. And when we focus on this one, we're going to ignore everything else. So essentially, take a touch means step back and loosen up the problem a little bit. And what we're going to do instead is we're going to call it Narain sequence. Look at Narain sequence, where we're just finding a sequence such that the mean of the terms a1 to an is an integer, or this sum is divisible by n for every single n. That's Narain sequence. Okay. Playing around with different types of sequences a little bit, you might eventually stumble across this Narain sequence. It's a sequence of odd numbers 1, 3, 5, and 7. It's a pretty basic sequence, and the simpler our solution is, the more likely it is to be correct. So we're headed down a right path. A nice thing about this sequence is the sum of the first n terms is n squared. You can check this yourself. So 1 is 1 squared. 1 plus 3 is 4 squared. 1 plus 3 plus 5, 9 squared. You get the idea. The mean, therefore, of the first n terms is n, which is an integer. And we're also going to look at the new sequence ai minus I, since that's also important for this question. That's the main thing we have to focus on. And as it happens, it turns out to be 0, 1, 2, and 3. Okay, that's quite nice, because if you remember, the sequence asked us to prove that this new modified, we'll call the sequence BI, and I'll just refer it to as the B sequence. The question asks us to prove that the B sequence contains every integer exactly once. And our B sequence doesn't satisfy that yet, but it contains every non-negative integer. It just doesn't have negative integers, which is a problem, but we can fix that. So, okay, we started by defining a new sequence. And this will happen because we took a step back. We took a touch. Okay, now we have a new question to handle. We got to go back to the original problem. And the original problem, the only difference is each an is the smallest positive integer. Here, as you can see, we don't have that because otherwise we'd have 1, 3, 2, 6, and whatever. I remember this sequence. That 1 hour calculating it forged it in my head. So, okay. This is where we introduce a principle which is called smoothing in Olympiad maths. The general idea is if you don't like something, turn it into something you like. Like, control things, make things happen the way you want them to. I've used this for about half the questions I do. Not the ideal method, but here it is really nice, so that's why I'm showing it. Okay, so now we just take out the AI and the BI sequence, and we want to see what happens when we smooth this, when we make it into a sequence that we like. So let's start by writing out what Matthew's sequence actually turns out to be. So that's, as we said, 1, 3. The next one that would make the mean an integer would be 2. After that, it will be 6. After that, it would be, we add 3 to get 15, but 3 is taken, so we get 8, etc., etc. And now, what we're going to do here is take this sequence of odd numbers, and if a term doesn't match up with Matthew's sequence, we change it. So that's exactly what we're going to do. We look 1, 3. We see that 5 is clearly not the smallest. 5 is not the answer to our problems. And we change it to a 2. But notice that the BI sequence also changes. In particular, we've changed the third term, and we have to reduce it by 3. I'll just give a quick explanation of why that is. So we have n dividing a1 plus a2 plus an. So this sum is a multiple of n. So if we subtract n from it, it's still a multiple of n. So what we do is we're just subtracting n from an. And we know that this is the smallest possible, since look at each of these ai. We have ai equals 2i minus 1. And this is less than 2i, right? So there is only one other possibility. Like, you can only subtract I from 2i minus 1 one time before it becomes a negative integer. We're given that this sequence is positive integers, so that's just absurd. And we can only subtract n one time, so we know that when we do, it is the smallest possible integer, and it is Matthew's sequence. Right, okay. Where were we? Yeah, we were looking at what happens to the B sequence. Okay, so notice that 5 becomes 2, so the 2 becomes minus 1. Love it. We've introduced our first negative number. And that's good news. That's good news because we're one step closer to getting every negative integer. But also, Notice that we have to make some other reductions, right? Because we've had this sum a1 plus a2 plus all of the rest, plus an minus n. And that's still divisible by n. But when you add n plus 1, remember that the sum of a1 plus a2 plus all of these other numbers in between plus an plus 1. Remember that that sum is a multiple of n plus 1. And when you subtract n, you have to subtract 1 more to get another multiple of n plus 1. Because, look, when you have n plus 1 divides k, n plus 1 also divides k minus n minus 1. We subtract that extra 1. So we go ahead and do that. And we have to do it for the rest of the upcoming integers by the same logic. So the 7 becomes a 6, the 9 becomes an 8, the 11 becomes a 10, and the 13 becomes a 12. Okay, and we've filled in the gap of positive integers that we've left by reducing this. So notice we lost a 2, but the 3 becomes a 2, the 4 becomes a 3, the 5 becomes a 4, and the 6 becomes a 5. We're really, really close. And notice that when we do another reduction, so what's the next one we can do? 6, reducing that by 4 by n, it's because it's the fourth term. 6 minus 4 is 2, that's already appeared. 8 minus 5 is 3, that's already appeared. But 10 minus 6 is 4, and that has not appeared. So we make that reduction, and we minus 1 from every subsequent term. And look at that, the same thing has happened. We've introduced the next negative number, so now we have minus 1 and minus 2, and we filled in the positive integer gap. So, from what we have, it seems that it's enough to show that there are infinitely many reductions we can do to get to Matthew's sequence from Narain's sequence. And this is quite a nice part of the problem. The final step, here we go. So, okay, let's say that we've had some finite number of reductions. We've had k minus 1 reductions. I'll make that a little bit clearer. K minus 1 reductions. Notice that after one reduction, every term after it becomes 1 less. After 2 reductions, every term after it becomes 2 less. So we went from 13 to 11. That means after k minus 1 reductions, every term after the final reduction, so let's say this point here is the final reduction, every other term becomes 2n minus k. So we have an equals 2n minus k eventually, right? Now, if k is even, an is eventually always even. But if k is odd, an is eventually always odd. So all terms have the same parity. Parity just means whether it's odd or whether it's even. All terms have the same parity. Okay, so what happens when we try to reduce one of these 2n minus k terms? What happens when we try and do that? 2n minus k is an, and remember that a reduction, if we go to some previous slide, a reduction is subtracting n. That's all it is, subtracting n. So if we try and shrink the value of an, we get n minus k. Okay. And, okay, so let's just say that all the terms are odd eventually. They have the same parity, so we can assume they're odd. The argument is the same if they're even, so don't worry about that. We know that every term before it becomes 2n minus k is less than m, because there are finitely many terms. So if there are only, say, n minus 1 terms, then there's only finitely many, so there has to be a maximum among those terms. Okay, so we can choose an n such that, okay, I'll write this here. We've assumed all the terms are odd, argument is the same if it's even. And we have a maximum for the previous n minus 1 terms that don't obey this 2n minus k rule. We can choose a big number such that this quantity is, or actually, I'll use d so that we don't confuse it. We can choose a big number d such that this quantity here, d minus k, once we reduce the term ad, is even. So it's not odd, so it doesn't appear in the 2n minus k section, and it's bigger than m, so it doesn't appear in the first n minus 1 terms. This means d minus k has not appeared in the sequence at all, and we can shrink it. So what have we done? We've started by defining a new sequence, which is stepping back from the problem a little bit. We've then showed that if we can find, we've then found an operation that gets our new sequence one step closer to the original sequence we want. We then showed that if we have infinitely many of those operations, we're done. So we assume that there's finitely many and arrived at a contradiction. Hence, there are infinitely many terms. We have all negative numbers appearing in the sequence, and we're done.